Hello, hello.
Next, we have Kemal Aziz from Rutgers University presenting on magic and entanglement transitions and quantum circuits with long range interactions. You can go ahead.
Okay. Hello, my name is Kemal Aziz, and I'm from Rutgers University. And I'm going to be talking about some work I did with my advisor and some collaborators at Rutgers University. And here you can see us over here arranged in like order of increasing happiness. And what I'm going to be talking about is the Clifford plus T simulations in all-tall quantum circuits. And specifically, what I'm going to be talking about is a new method to represent the full density matrix of a state which undergoes evolution with Clifford and T gates. And so some motivation, it's well known from the Gottesman-Neal theorem that quantum circuits, which consist of C-naught, Hadamard, and phase gates, which are known as Clifford gates and Pauli measurements, can be efficiently simulated on a classical computer. And this is known as a stabilizer circuit. However, stabilizer circuits are not universal, meaning that any arbitrary quantum circuit cannot be written in terms of Clifford gates and Pauli measurements. However, when you combine Clifford gates with the T gate, which is like a pi over 8 rotation, it's well known that this forms a universal gate set for quantum computation, meaning that you can decompose any kind of quantum gate in terms of Clifford gates and T gates. However, it's exponentially difficult to simulate the circuit in a number of T gates, meaning that the simulation time and also the amount of memory needed to store the full wave function will grow exponentially in the number of T gates. And so here I've just shown an example of something that's been studied already in the literature, where you have some brickwork structure of random two-side Clifford gates and T gates occurring with some probability, and you have Z-basis measurements, and this circuit is hard to simulate. However, if you remove the T gates, then you have like some kind of random Clifford circuit, which is non-universal, but this circuit is easy to simulate. So this is the reference for the work. So the circuit model that we looked at was adapted from this paper by Sagar Vijay. And basically the idea is you start in some random product state initialized in the X basis, and you have like some long range CZ gates and Z basis measurements. And so in this model, the Z basis measurements actually kill the T gates. So if you have a T gate preceding a Z basis measurement, it's as if you have no T gate at all. And also the T gates commute with the entangling unitaries. And so what this means is you can basically push the T gates to the back of the circuit because they commute with all the unitaries, and also they're killed by the Z basis measurements. However, in this model, the T gates act trivially because you can show that if you can push the T gates to the back of the circuit, the entanglement of the state is unchanged under T gates, meaning if you put in T gates, it has no effect on the entanglement spectrum or the entanglement of the state. So what we did is we took these Z-basis measurements and we changed them to X-basis measurements. And you can see in simulations that when you have an X-basis measurement, the T gates will actually change the entanglement spectrum of the state. And so what we did is as I'm going to explain, is we developed an algorithm to efficiently simulate not just this circuit, but we use this circuit as like an example, but to simulate the full density matrix of this circuit, specifically up to 64 qubits. And so just like a quick overview of some previous methods of like these Clifford plus T simulators, the idea is you have some stabilizer state, and then when you put the T gate, this will sort of act like some kind of, almost like some kind of error channel that has three different Clifford operations. So it will basically like fork your Clifford state into like three different stabilizer states. And that's because of like this channel over here. And so the idea is if you want to sort of estimate observables that are linear in the density matrix, what you do is you sort of sample each of these trajectories with some kind of, weight or probability. And then you can sort of estimate the value of your observable by taking a lot of like Monte Carlo samples. And so what we did is we want a way to represent the full density matrix of the state. So here, this is like some stabilizer state. And basically what a stabilizer state is, it's like a product of projectors onto like Pauli operators. And what we do is we augment this with like some logical operators, which are just some tensor product of like local polystrings. And so the idea is like, so if you want to hit this with some unitaries, because UDagger use just the identity, basically what you do is you just update the stabilizer tableau and your logical separately. And for Clifford unitaries, basically they map poly operators onto poly operators, so the size of your representation will not really increase. But under T-gates, the number of logicals will grow exponentially, so it becomes harder to simulate because the number of these will grow. And the idea is very similar under measurements. However, with measurements, because you're measuring a poly operator, that can actually decrease the number of logicals and make your circuit easier to simulate. And it's also you can also calculate the entanglement from this representation. And so to benchmark this algorithm, we looked at something called a purification transition. And the idea of a purification transition is you have like some ancilla qubit, and you couple it to your system, and then you basically grow the entanglement between the ancilla and the rest of the system by acting like some random Clifford gates on it, and then you just run your circuit. And the idea is as you run your circuit with measurements, the entanglement between the ancilla and the rest of your system will decay exponentially with some like decay rate tau. And you can like identify a phase transition in the reduced density matrix of the ancilla. So when the ancilla is like decoupled from your system, the reduced density matrix is sort of like a pure state, but when it's entangled, it's sort of like a mixed state. And so like there's like this transition between like pure and mixed states of the ancilla that you can sort of locate by locating the inflection point in like this decay time tau as a function of system size. And so here on the left, these are some stabilizer simulations, and you can also like extract like, critical exponents of your phase transition by doing some kind of scaling collapse. And so the idea is in the literature, it's sort of been studied, and for the Haar-Random case and the Clifford all-to-all circuits, sort of the exponents are expected to be the same. So this gives us a way to sort of check our simulator. And so over here, what we've done is we've added T-gates in these four like charts, and basically you see that the critical exponents are the same, and also like the critical measurement probability is the same. And so basically, what we want to do now is you want to like sort of characterize like how difficult it is to simulate the circuit. And there's this quantity called magic that tells you how difficult it is to simulate your circuit. And basically you can think of it as like a metric that gives you like the distance of your state to like a Clifford state or a stabilizer state. And so like, why do you want to look at magic? Because it's well known that you need entanglement for quantum advantage. Because if you have like states with low entanglement, you can simulate that using MPS and like other methods on a classical computer. However, having entanglement is not enough. There are a class of states that are highly entangled. Like these stabilizer states have a lot of entanglement, but you can still simulate them efficiently on a quantum computer. So basically you need entanglement and magic for like in order to achieve quantum advantage. And so basically now I'm going to like talk about a way to compute the magic in these circuits. And the idea is you can make like 2 copies of your circuit, and then at the final time step you do a measurement in the Bell basis, and then you can sample these states like by looking at your measurement outcomes of like the 2 copies of these state. And the idea is when you do these Bell measurements, it's equivalent to saying that you have like some poly operator in your original state, and you're looking at like what's the probability of obtaining this poly operator given some state. And you can show that if you do this like this method of making 2 copies of the state, that's equivalent to sort of finding these poly operators. And so the idea is you want to use these Bell samples that you get in order to characterize the magic, or like how close it is to a stabilizer state. And so the idea is you have these samples, and then you form like all the possible, so like these are like generators of some space. So you take like all the possible products of these samples, and you basically look at the dimension of the space. And it's well known that for stabilizer states, like the dimension of like these poly operators you sample is just your system size or how long the circuit is. But for like Haar-Random states or states that are not close to the stabilizer group, like the dimension of this poly space will grow. So under T-gates, like this measure of magic will be increasing. And so the idea is like we want to develop like some kind of algorithm to efficiently simulate these poly operators. And so basically you can write down the density matrix of your state as like some kind of mixed stabilizer state, multiplying like some other product of poly operators. And you can show, if you just write this out, as a sort of equivalent to like some superposition of stabilizer states. And the main idea is like the samples, the Bell samples, are just basically like products of these Pauli operators. So if you write down the density matrix in this way, you can efficiently find all of the Pauli operators. And so here I just like show like some like plot, just like benchmarking our algorithm and just showing, so, okay, and showing like how efficient our algorithm is in like obtaining these Bell samples and computing the magic. And so the idea is the total number of Bell samples for a given density matrix is like exponentially large. So it's between 2 to the L and 4 to the L. And so the idea is our algorithm works for a small number of samples. So tau is like the number of Bell samples. And so you can see that even though the number of Bell samples is like astronomically large, the magic is converging in a low number of samples. So this method of Bell sampling is sort of like sample efficient. So it's sample efficient. So that's the idea here. And so the conclusion, we develop a new algorithm to represent the full density matrix of the state under T-gates and measurements. And we sort of benchmark our results against an all-to-all circuit model. All right, so that's it. Thank you.
Questions? So could you re-explain your why your Bell sampling only required fewer samples, or it seemed to mention that you had
Oh, yeah, so the magic converges in a low number of Bell samples. So basically, like when you add Bell samples, so basically like the dimension
okay.
of the
So you
space
don't
is
need
like, you don't need a lot. Yeah.
Okay.
That's
All right. Thank you.
I think.